the invitation, the chance to be here. I thought I would use this time to do what I like to do, is just kind of wildly speculate about some things and leave details to others, hopefully. And towards that, there's two things I want to talk about. One is, can you get optical cycling centers or do optical cycling in molecular ions? Seems like an easy thing. I'm going to start with a statement here that could be provocative in this conference, is that you shouldn't actually shine a laser at a molecule. It's a bad idea, and I'll say why. And the story here will be, it's a little bit more challenging than I expected to find good molecules that are ions for cycling. And then I want to try to ask a question. And you'll notice that I didn't say I want to try to answer a question. I'm going to try to ask a question of, is a quantum functional group possible? And talk about that. All right, I sort of plan on running out of time, so I thought I'd do this first. We're really fortunate to have a great team of people working together. Wes, of course, here, constant co-conspirator. Justin and Anastasia are two amazing physical chemists who've really committed themselves to learning how to speak our language, and we're really thankful for them. Nick, you guys know and love. This guy I think you've heard of. Anna Krylov is here, is a big help as well. Okay. All right. So laserless quantum logic. So what do I mean by this? So the great thing about molecules, right, are they interact with a huge range of frequencies, megahertz, gigahertz to terahertz. And by terahertz, I mean, like even hundreds of terahertz. So I like to say, the megahertz regime is very calm, collected, it's controlled, we know what's going on. As you go to gigahertz, things get a little more interesting, right? But depending on where you're at, things are still kind of under control. And in the terahertz regime, things get very. So for those of you that actually know, this is Gary Busey. The rest of these are Nick Nolte. You can't tell. And what do I mean? What's so bad about the terahertz? Well, the sources of electromagnetic radiation are worse. There's suddenly, you open all these vacuum channels, or you can scatter photons, you have Raman scattering errors. These are really bad. If you look in trapped ion quantum computing, which is really advanced in what can be done, photon scattering errors are the problem. So it would be nice to be in this sort of gigahertz and megahertz regime. And of course, everybody knows between early career Nick Nolte and middle career Nick Nolte is Wes Campbell. And so Wes and I spent the pandemic coming up with a bunch of crazy ideas. These are the two that are probably good. The rest I didn't put up there. And these are all about how to do all the tools you need for quantum logic, but without using lasers. And you can do that in molecular ions, right? Because you don't need the lasers for trapping and cooling. So, however, everything in moderation, right? You do need state preparation. And measurement, I think you can do without lasers, but you do need state preparation. And there, I really don't know of a way to do it better than to access the vacuum, because a photon can take a lot of entropy with it when it goes away. And that's really the best way to do state prep. But because of this means that our criteria for optical cycling are much more relaxed for ions than you would need for neutral molecules. You don't expect to really have to have fast scattering rates, because you're just doing, optical pumping, maybe state detection. You don't need amazingly diagonal Frank Condon factors, because the ion's going to be there no matter what, and you just kind of, take your time with it. You do, I think, because we like these experiments to continue without reloading ion traps and all of that, you kind of don't want to be able to dissociate or ionize or pre-dissociate the molecule. So I think that's really important. So we set off to tackle this with the folks here. So Maxime Ivanov, Pavel, who spoke earlier today, are in Anna's group, and they did all the heavy lifting here. And the basic idea was, look, in the sort of neutral molecule OCC world, there's a couple of archetypes, but the most tried and true is, let's take an alkaline earth, bond it to a halogen. You get a nice ionically bonded thing with this non-bonding electron above it that just has everything we want. So we want an ion. What do? Let's just kind of move over one column, right? So now when you ionize scandium or yttrium, you end up with a calcium or strontium, effectively. Bond it to this halogen, and you should be fine. So that is this first framework here, which is this A represents, sort of the metal, and this will be the halogen in this case. So it's sort of an A2 plus with a B minus, and the dot means where the cycling center resides. In addition to what I've just showed you, like scandium fluoride, all these other combinations we checked as well. So, maybe the cycling center maybe it should be A neutral with B plus, or maybe the cycling center should be distributed across the molecule. Just different ideas you could think about of like, how could I possibly get a cycling center? And the result, I think, is summed up nicely in this picture that Maxime made. When you submit to these chemistry journals, they often ask you, make a little graphic that tells us the main point of your research. And this is what Maxime made. So if you want to laser-cooled neutral molecules, the road is, nice and open. But for ions, it's a bit more hazardous. And why is that? Just without going into too many details, they're just generally less diagonal. What tends to happen is they're just more sensitive to the excitation of this valence electron. You can think of it, I like to think of it as the location of the charge matters. So, in, say, strontium fluoride, you're exciting this thing above this ionically bonded but neutral thing. Now this thing is ionized as well. If that shifts a little, when this thing excites, it can move that charge, and then the bonding changes. So this is just much more sensitive to the details. You also bring in D states anytime you go into this D block, and those are kind of a problem. All right? I mean, like in YO, they can be good, but since the Frank Condons are already not great, they just end up making it a little too complicated. Many times you even get delta states as your ground state for these molecules, and it sort of switches. And so the quick takeaway, in my opinion, is that Brian Odom and Kim Brown really found the good ones already that we know about. And they just did this through brute force literature searching. I do think, I don't want to say the book is closed on this. There are no diatomic OCC molecules beyond these. Maybe other people have ideas about it, but it was surprisingly more difficult than I sort of thought it would be. Okay, so that's what I wanted to say there. And now, there, this stopped working. I want to, I guess there's one other thing I should say, actually. So Brian Odom, as many of you know, has done amazing work with silicon oxide plus. He's able to optically pump it, prepare it in a single quantum state, in these ion traps and do things with it. This is for the schemes that I sort of flashed up earlier for this laserless quantum logic. This is actually a pretty bad qubit, I think, because old me would have been very happy that there's no hyperfine here, but the new me is unhappy that there's hyperfine. It's the same sentence, but you read it with different inflections. You really need hyperfine if you're going to store quantum information anywhere. It's the rule of life. And so what we did was say, look, if you go to 29 silicon oxide plus, you have a nuclear spin 1/2. You get F equals 0 quantum states. Those of you that have worked with molecules with F equals 0 quantum states know how great those are. It's magic. And so this is really a nice qubit. But of course, like everything, no one had ever taken the spectroscopy of this molecule that you want. So we went and did that. You could resolve all the hyperfines and then work out the structure. And I'm not going to spend any time on this other than to say the structure is now known. It's really nice. We expect coherence times much longer than 1,000 seconds. And there's some really nice features here. Because the hyperfine interaction is so strong, you get approximate delta G equals 0 selection rules. And you can use this to do state preparation of, say, this single quantum state by scattering like one photon with like 4 nines of fidelity. Okay. All right, so now I want to switch gears completely back to neutral molecules. And this will be sort of following up on what the great talk we just heard from Ben about calcium phenoxide. The question I want to ask is, how big can you make an alkali atom? Right? So everything at this workshop has been an alkali atom, effectively, right? Calcium fluoride, strontium fluoride, YO, it's all just alkalis in a way. How big can you go with this? Right? Well, you guys all know this paper is one of the first really to ever consider this. I put it up because I thought this was awesome. They say, we pointed out that this could work, basically, and then the reference is to a meeting here 11 years ago. So that's kind of neat. And the idea is, that's when they, you guys may have heard that this worked out. The idea is, again, you want, something that will really pull an electron away from this alkaline earth, leaving you this non-bonding electron. And so this paper, I really want to highlight. I know Claire's going after me, but I want to brag on her because she may not. I find this paper really important, and it was really influential in, I think, how we think about things. What Claire explored was to take these phenol molecules, put a calcium atom on them, and then just see, because organic chemistry is magic, and you can just put anything you want here, like you can literally buy it. You call up Sigma Aldrich and, I want a Ford F-150 in the 4 position, and it shows up in the mail. Just to explore, like, as you substitute, what happens, and can you tune these Frank-Condon factors? Right? And what she found is shown in this graph here. This thing, Hammett total, it's some crazy chemist thing, but what it really means is how ionic is this bond, and this is kind of like how electron withdrawing is this thing is kind of over here. And so the more you make this thing electron withdrawing, the better the Frank-Condon factors are. And so these are all different molecules that she tried by putting different things here. So we went in the lab to study this. We repurposed a CBGB we had for some interstellar chemistry that Wes and I were doing. And Guozhou was really the hero of the story. Guangming is their amazing team. They've done a lot of great work. They set off and took some of the first spectroscopy of this. They then called up Sigma, and for those, if you're keeping sort of score at home, if you know about calcium fluoride, strontium fluoride, it's kind of the same thing. It's kind of like the doublet pi 1/2, doublet pi 3/2, and you have this, these X to A and X to B transition. And you can drive this transition, look at dispersed fluorescence to get an idea of the Frank-Condon factors. And what you see is shown here. This is very similar to the graph Ben showed for a dispersed fluorescence spectrum. This wave number is relative to the excitation wavelength. So here's the strong diagonal decay, and then these are all just the other vibrational modes that happen. You can make some sort of bar graph. You can worry a lot about systematics and did you see all the modes and try to get some vibrational branching ratios. And what you find is that this thing is, in the high 90% diagonal. You can then call up Sigma Aldrich and just order a bunch of different things and just see how they all look. At the end of the day, we wanted to organize this and all put it on one graph. And Guozhou came up with this idea of plotting it versus pKa. pKa is kind of like the Hammett total in that it at least correlates with the electron withdrawing power of this, but it's like the acid strength. It's like something you can go measure in the lab. So it's a little bit easier for, it's a little more relatable of a thing. And what you see right away is something I hope you come away with, is that molecular complexity isn't always like optical cycling complexity. This says qubit because I recycled this from a quantum computing talk, but and I was lazy. But it's not, the complexity of the molecule doesn't translate into like a complexity in your lab necessarily. And this is a beautiful example of this. So this is just the excitation energy of these molecules. Red is X to A, blue is X to B. And as a function of pK, it's literally a straight line. And it's such a good straight line that if we want to go try a different molecule, we say, where does it fall on GZ's line? I call this GZ's line, Guozhou's line. And you can find the molecule within a few minutes. It's much better than theory, but no offense, Claire. It's literally AX plus B. And, you can also look at these vibrational branching ratios as a function of pKa. And here we've drawn the structures just so you see like which one each of these are. Now, the prediction is that there should be some upward trend with pKa. And if you believe in statistics, it would be hard to say that here. Like you could fit a line and it would go up probably, but after staring at this a while, I sort of tend to believe it. And let me tell you how I've come to that sort of conclusion. A lot of these things really mess up the symmetry of the molecule. You know, having a CF3 over at some angle just really lowers your symmetry. And that also comes into play. So I sort of see in my mind's eye, like, you know, there is this trend that we expect is probably there, but, you know, messing up the symmetry is something that can really change your vibrational branching ratios. 5 minutes, okay, perfect. Is that like 5 minutes till I'm done? Or like including questions? Yeah. Okay, cool. Sort of, I think the most remarkable thing here is that, you know, in some sense, the most complicated molecule we looked at, which was this calcium phenoxide with the fluorine substituted on the 3, 4, and 5 positions of the ring, is the most diagonal. And it's like, you know, around 99% diagonal. The idea being here that you're really increasing the ionicity of this bond, making this look more like an alkali atom. And I wanted to highlight John Doyle here because this was a really important, or really fun collaboration with John. And this data was actually taken in his lab. GZ flew to Harvard, used their dispersed fluorescence spectrometer, took the data, promptly came back and built a copy of it in our labs. Thanks, John. So it was a lot of fun. Okay. We've also sort of looked at extending this. I won't talk about it in terms of time, but we've done now the strontium phenoxides. It's kind of the similar story. We've taken high-resolution spectroscopy, kind of just like what Ben showed for calcium phenoxide earlier. And Debayan here has also looked at this for adding one more ring, these sort of naphthols. And this situation is very similar. They, again, have high vibrational branching ratios and, you know, seems sort of simple to explain. All right, so in my last second, I want to leave you with a question. And the question I want to leave you is not how big can you make an alkali atom, but it's, is a quantum functional group possible? And so what do I mean by that? It can mean a couple of things, and I probably mean all of them when I say that, especially if they're good ideas, and that was exactly what I meant. But what I mean is there a group of atoms or molecules that I can attach to anything, and it's going to be a decent cycling center, maybe even a good one, right? I could use that to store quantum information, or maybe I just use it to learn about the thing I'm attaching it to sort of witness what's going on in that molecule. You might say, well, this calcium oxide thing looks good so far. Does it work? Could it be that simple? And Claire has showed us that it breaks here. What happens is at this point, excitations in this ring structure become roughly the same energy as in the alkali. So when you excite, the excitation is just distributed over the whole thing, and the Frank condoms just break. They go from like 90% to like 0.3 or something. So this doesn't do it. So what we're thinking about now are other structures that maybe could do that. These are shown here, sort of, you know, how isolated can we make an OCC? We're starting to think about what happens if you put multiple of these on some molecules. And the thing I'm really excited about is what about putting these on like photochromatic or photochromic switch molecules? These are molecules that I can hit them with light and make them like do this. Like what if I have some cyclic centers here and I like say, okay, now you're in this conformer. Now you go back. Like what are the things you can do with this? And then I will just quickly skip a bunch of stuff. Oh no, I timed it right. And so, yeah, let me stop. I told you about the optical cycling center and ions. If you have ideas there, I think you have a willing community that would love to know about that. Then I hope I excited you about making optical cycling centers more generic. All right, thank you.
So this photochromic centers you talked about, do they do that in solution or isolated molecule?
So an isolated molecule, you'd have to do like a Raman transition, like a styrap sort of thing. I mean, it's basically like there's Dave, when they took the long-range diatomic molecules and transferred them to the ground state, you do that with styrap. You could do the same thing to like drive a Raman transition from this to this, I think.
So it's not a vibrational mode, it's just, or it is a vibrational mode?
So there are in this other conformer vibrational modes, and that basis is different than this one. Yeah.
So, quick question. I don't know that much about ionic or anionic beam production, so this question might be kind of silly, but you said you could go one to the right and make it, and then have it be ionized. Could you just go one to the left and have it be an anion?
So you can do this, and it actually is not a bad idea because that anion, that electron, probably really doesn't affect the bonding very much. The issue is that it's very easy to photodetach that electron, right? Like, you excite it, and then boom, it absorbs another photon, and it's ionized, or they call it photodetachment when it's an ion. But I think it's a possibility. Pardon?
Are there any anions that are
So
or be unlikely to do that?
I believe the answer is yes to that question. Yeah.
We have time for one more question.
Oh, somebody down there.
Yeah. Shane?
Yeah, so I remember from the earlier talk this afternoon that what actually matters is these weak transitions. So here, is it more at the exploratory stage, or you're thinking more about like some other way to get these molecules code and then use these?
So the weak transitions can certainly matter if you're trying to build a MOT of these things. If you're trying to do other things, maybe they're less important. So the answer to your question is, of course, those matter, and people will have to worry about them if they go try to build a MOT of these.
Let's thank Eric.
All right, thanks, guys.